So in boosting, as we talked about, we select the training subsets instead of like randomly choosing them, like in bagging. We use algorithms to identify that. We choose subsets for learners that where other learners are performing poorly on, and then like obviously there are many variants. However, the one that I kind of described earlier is the AdaBoost one, which is a more recent algorithm, like not as old as these like more hand-driven ones, and which is kind of famous, but there's so many different variants also now, like many more boosting algorithms out there that like are performing better than AdaBoost, and like are just adaptations mostly on AdaBoost. But there's a large part of the machine learning literature on improving and making boosting algorithms much better. Okay. I think we talked about this quite at length, so we don't really have to spend much time on this. And so for we can also kind of like generalize this stacking, where we now extend the voting scheme of basically just counting or saying like, oh, I want the maximum, I want the minimum, I want the mean value, where we can now kind of like generalize this to basically learn another classifier. And in this case, the fusion is now by itself a classifier. I mentioned that earlier, that you could actually consider that to be a learnable classifier. And for example, you could learn a multi-layer perceptron in this case. However, what you would want this learner to learn off of is not the data that these guys have seen before during their training. So what does that mean? So basically, you learn the classifiers, like you learn the set of classifiers maybe on the global data, and then they produce outputs. And they produce a whole bunch of like predictions for each class separately, and like they could, for example, produce so like the first classifier, D1, produces like, for example, 0.2, 0.3, 0.5, and then D whatever I produces 0.8, 0.2, and 0, right? So that could happen. So they are pretty like they don't agree at all. So this guy says 0.2 for the first class, but this guy says 0.8 for the first class, and this guy says 0.5 for the third class, and this one says 0 for the third class, right? So what this means is basically that they are disagreeing on some items, and what the opportunity here is that you can actually learn to correct for such errors. And it might happen, in fact, that in your data, for whatever reason, that when these two classifiers disagree, it's actually the middle class, or it's actually class 1. Okay, so that is something that you could learn from within this classifier here. So that's kind of error correcting up there. But what is important here is that you don't train this on what the outputs are for these guys, what they're trained on, because that would basically just like enforce an overfitting in this classifier here. So what you want to do is you want to train these on like a separate set of data, and then you want to use them as kind of like prediction producers, and then train this guy on the produced predictions on a separate set that you held out before, right? And it could be a smaller data set. So that actually then allows you to learn, for example, these kind of like patterns of like confusions and yeah. Is that clear? So you just want to train them on different data sets. Yeah. So one tip, one for example as a classifier here would be decision templates, and it's a so-called decision templates classifier. Just gonna briefly explain that one. Don't really have that in the slides. But decision templates, in principle, are the following. You just basically, if you have, for example, only like each classifier produces one number between 0 and 1, and so your classifiers produce the following prediction, something like that. So this is 4 classifiers produce this output, and then you would store. And so the classifiers are now trained on a separate data set. They're trained, they're fixed, and now this is like the new data set. And you would take this as a vector and store it wherever the class was. Like you have like either 1s or 0s, and you would store this either in the list of samples that belong to a class 1 or samples that belong to class 0. Okay, and then you would just have like a whole list of those, and then what you can do now, so now you have like a 4-dimensional vector in each of those rows here, and you could do, for example, k-means, or you could do other clustering methods. You could and you can basically use a nearest neighbor. So like for the testing case, all of these produce an output, and then you just look, okay, which template fits best in either of the lists, and then you say, oh, this template here fits best. That's why we're saying this is a 0 as a class as the output. Okay, so that's kind of like one way to deal with these as well. So this is like a very simple learned classifier on top, where you don't really have to do much except for store all the patterns and then identify which one's the nearest neighbor or which one fits in a k-means in those spaces. Does that make sense? Okay, so that's kind of just, and what I'm trying to kind of explain in that sense is that you can be really creative with how you fuse and how you make these decisions here. You can train anything up there. You can train MLPs, etc. So one example that we used is this one here, where we had 3 separate classifiers that produced a continuous output, and then we utilized this output that they produce in the classification of a new collected output. And the idea here was that for example, RK prime and RG prime are then refined to RG and RK, because these are like vocal tract parameters, and we first try to approximate them independently from each other, but because the vocal tract is not, like all the parameters are not independent from each other, we also then try to learn them together in a second stage so that we can refine it and can make it more according to more appropriate according to like the theory underlying the vocal tract analysis and simulation. That's just an example. It's like, but then you can also with Fusion you can go multi-stage. You can learn more and more layers. In this case, what we did is the following, where we had like a basic layer that like, gets information from all these sources, and the basic layer basically makes decisions on a very short time scale, while then the second layer then integrates information over multiple classifiers over time. It makes a decision that is now like has a bigger lag, and it has like basically like a bigger time window to make assessments on, and then you would have even on top of that, even like a further, much slower decision level, and so you can integrate over time in such stacks, and then you can be super creative with whatever you want to do here. Okay, so just a couple of words on fine-tuning. There's no guarantee that using multiple base learner will improve the overall classification. Base learners can be removed from an ensemble if they do not add to the accuracy, so you can basically identify in an ensemble of classifiers if they always say the same, they're super correlated with each other. You can remove one or two that have this condition, and basically do not lose out on performance. Ensemble selection again can become quite difficult. So you could, for example, combine every possible classifier combination and test them all out, or you can utilize some greedy approaches such as forward selection or backward selection of classifiers. So, for example, for forward selection, you would start with a single best classifier and add the one that adds the most until improvement stopped. In the backward selection, you just start with all the classifiers you want to investigate, and then remove the ones that are not helpful. To formalize this kind of idea, cascading was basically what I came up with, where you have the same input going into the first classifier, then the classifier decides if it was certain or uncertain about the example, and basically if it was certain, it produces an output and the cascade stops. If it wasn't, it basically moves on to the next one, and the next one already has the decision ready. Basically, this is kind of like the X already goes to all the classifiers at the same time, and then each classifier just says like, yes, I know what it is, or no, and then like you just stop the cascade wherever you are reaching a confident decision. Okay, so that's kind of like the idea of cascading. And in contrast to AutoBoost, we do not just select the instances of previous classifiers was wrong on, but also all those that it is not confident on. So so here you need to have a decision that the classifier actually is uncertain about. So even if it was right, you would move on if it was uncertain about it. Okay. Then to formalize or to give a couple of like pros and cons about decision versus feature level fusion. So we up to now have kind of looked at various ways to combine learners, which is basically decision fusion or late fusion. But this is not the only approach. We can investigate, for example, feature level fusion, where in this example, all the features are first concatenated, and then this big vector of features goes into a classifier, which then tries to classify this. There are a couple of pros and cons. The pros, you only have to learn one single classifier, and the search space for optimizing this classifier is much reduced, so you don't have to come up with the correct set of hyperparameters for each base learner itself, but just for one big learner, you try to come up with the hyperparameters that optimize your results. However, sometimes it's difficult to merge data from different sources. So we talked about this briefly, where I said that video sources or video information is not necessarily synchronized with acoustic information. There might be delays and so on. So it might be difficult, and it also might be that the classifier might be very complex due to the high input dimensionality. All right. And then, but like late fusion and early fusion is not the only way to combine classifiers, as we said already. You can come up with various ways, and like you can see, like for example, where you basically have analysis units. Here you have like a feature fusion thing, like analysis unit, or like a decision fusion analysis unit. So you can have like this typical early fusion, you can have the intermediate kind of fusion, and then like various mixtures of this. So there are like many different ways to look at fusion techniques, but obviously the more and more complex you want to, like, or your choice is, the more complex your search space for the optimal parameters will be, and you'll run into difficulties finding the right set of parameters that optimizes your problem. So sometimes it's better or easier if you just stick to that level if you want to do multimodal fusion, or want to do classification first and like identify, okay, so this is how good I can get in this world. Maybe now I add another complexity step to the problem, but it might not really pay off. Like it's often just a trial and error kind of game in this sense. There is no given theory about like what will, like, given your data set, like there's no way you can like early on know what the right approach will be. If you have ideas about your data, if you have ideas about like what the underlying structure of your data will be or looks like, then you can easily or like better identify which structure will be likely helpful. But yeah, so use your top-down knowledge on like what approach to use. To go on with a few more challenges, and so this is kind of like challenges of multimodal fusion, just to visualize this a bit better. And so basically to combine, how do you combine outputs of base learners for maximum likelihood, and how to generate base learners that complement each other. We talked about the analogies, or the analogy of diversity, and I already mentioned that this problem was not successfully approached because the acoustic and the visual domain while speaking was highly dependent on each other, and was not actually, if you want to try to find that audiovisual speech recognition paper, it might help you like locate the link. Okay. I just thought of it. But I can try to find the citation for this as well. But it should be like automatic, like audiovisual speech recognition, something. I can try to find it. And yeah, we talked about this. I don't know why I have these slides double in here. Yeah, we talked about intermediate fusion as well, where you can basically fuse a few decisions and then fuse again and so on. But then I would like to show actually these slides here. These other ones must have slipped in, where you don't just fuse information at a time or at a single time point across multiple modalities, but you can also try to fuse information over multiple data points. So for example, you could imagine the following, where you have a linear or logistic classifier and you make a couple of observations. Why is this not that? Okay, so you make a decision here over this time slice, you move a step, and you make a bunch of observations, etc., blah blah blah, and then you basically fuse the information over all of these time steps to make a decision where something happened. Yeah, you can use all these different types of classifiers that usually don't have access to temporal information to make an assessment over time as well. So you can like combine information over time by, again, averaging, learning another classifier, and so on. And before I just showed like how basically you would use a window and then slide it all the way to the end of the next window, but you can also have them overlap and basically make decisions like with an overlap of information. And then we talked about this briefly as well, just as a general kind of reference for your for the course. You have the data sources usually have different types of sampling rates. For audio data, you usually have a sampling rate of like 16 kilohertz. Like CD quality would even be like 44.1 kilohertz and so on. So like this, the audio is sampled at a very, very high rate, and you have quite a bit of data points. However, they are one-dimensional in the acoustic domain. But then you would usually kind of extract certain types of features from the audio that kind of reduce the sampling rate down to something more manageable. In this case, we extract like fundamental frequency values 10 times per second. Usually this actually should be like around 100 times per second, so that you have a selection, like one output every 10 milliseconds. Okay? So you have like a sliding window of decisions for with every 10 milliseconds. You can calculate these guys at, for example, 30 hertz because that's the video input. But then words, for example, is a bit more weird because that like you don't really have a frequency associated to language or the words. But you could, for example, extract the sentiment. If I say like a happy or a sad word in a certain area, you could select for this time span you have a sad word or a happy word. So you would extract features at a different frequency here. But then, like, how do you fuse all of these channels? Do you fuse it with the fastest? So what does that mean? Can anybody think of that? Like, let's say this is the fastest. 30 hertz. Let's not talk about the audio one because that's raw data. So if you have this and you use this as your basic like rhythm for classification, so you want to produce 30 outputs per second with your classifiers. What will you do with pitch, for example? That only produces 10 times per second outputs. Or you just basically either interpolate between consecutive ones, like you fill in the gaps, or you just keep the value constant over a certain time. So you would basically blow up the frequency of this one by either linear interpolation or whatever you want to do. More smart interpolation with the gradient as an input. But that, yeah. But you're just basically creating data, right? Which is obviously sometimes a bit funky. And then for the other way would be to use the slowest. So basically you would say, okay, whatever, I get a new word, I then give you like the average lip radius plus the average pitch over that time period where I observed that word. But now what you're doing is like you're slicing out data, you're undersampling your data, and you might actually lose information that you otherwise would have had access to. And obviously, sometimes if you, for example, just sample on words, you often don't even have data for certain areas. And for speech, the same. Like you always have a face, but you don't always talk. So there's another difficulty here. So when you do like multimodal fusion and this way, you have to think about these ways to combine. I brought a couple of examples. We can talk about them briefly. So one of them, we just saw like previously some slides on like the laughter detection. But I would like to give a very short overview of like back channels, which are kind of interesting. But what we're interested here are like basically these non-verbal vocal expressions, such as back channels, laughters, moans, etc. And we believe that they both have a distinct prosodic and vocal characteristic. So laughter, for example, ha 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 ha, or like back channels, or something like that. So they have a certain like acoustic pattern to them. And we could use the acoustic pattern to recognize those. But for example, also laughter is accompanied often with smiles or like certain patterns of the head movement where like the head goes up and down and so on. So to combine this information from these two separate domains might actually improve our ability to recognize them. And as an example, I actually just wanted to show you how fragmented actually conversations are, and it's another example how data can be visualized in kind of like fun ways. So what you're going to see in the next slide is basically each line is 1 minute of conversation, and the green boxes are when the green person speaks, and the red boxes is when the red person speaks. And this is how fragmented speech is. So what can we see? We can see basically that there are phases where the red person speaks and where the green person speaks and so on. But then we also always have like these little tiny like green dots throughout like areas where the red person mostly speaks. And this is kind of fun because this shows mostly back channels where a person says okay, yeah, and to actually find those has quite a few implications sometimes, because if you have a lot of these back channels, it often signifies that the person is actively listening, is not disengaged from the conversation, and so that has some impact on the ability to identify like good or bad conversations. So that's kind of cool as well. And that's just an example. And then for laughter, told you that laughter is kind of multimodal. We have something visual, we have something acoustic. It's very important across cultures, and we try to set out to detect laughter in multi-party conversations that look like this.
Memory to remember people's names.
Yeah,
and it's,
right.
it's very embarrassing. You try to say, oh, I don't know how to call you.
Oh, just go sensei.
Okay, yes.
So we wanted to find these moments of like laughter and how they come together in a group, and this was done in Japan. This was my former supervisor there, Nick Campbell, and we tried to automatically detect these phases of where people like join each other in a moment of laughter or a moment of excitation, and we call it, like in Japanese it's called moriagari, and so we tried to detect moriagari. And the funny thing is that moriagari happens whenever, kind of like, and we didn't use this as a feature, but it's kind of fun to see that it happens often when all four speakers, well, there's another one, when all four speakers, or at least three of them, talk at the same time, or like basically talk very closely towards each other, and so that kind of like these are these phases of kind of excitement within a group that were very important. So yeah, this is a fun way to visualize data or conversational data. So what we used is basically a camera that was situated in the middle of the table, and it recorded 360 degrees. We didn't really have like high resolution back then. It's like 2007 or something. And we record mostly the face of these individuals, and then we had like a microphone on that camera too. So we had 2 input devices, and the conversations were about 90 minutes long, and they contained about 10% of laughter. So you can already guess, okay, like, oh, if I trained everything on like accuracy and I'm like 10% correct, then that's problematic, because 90% correct, well, that would be problematic. So we added different evaluation methods like F1 score. We talked about the fusion. We compared echo state networks, which are like these guys here. Don't want to talk too much about them. And hidden Markov models. We did some experiments with tenfold cross validation. We also had a test set that we held out. We never used and only used for the testing. And we conducted performance evaluation using like % absolute error and F1 score. Echo state networks, just for your reference, they're kind of cool because they can detect or they can learn patterns that are temporal. They are like very closely motivated through like a brain column of neural networks. So there's local connectivity, there's that is enforced, and like global connectivity that's not so much. But these guys, this is a form of neural network that can be automatically, it can be learned in a similar way like a support vector machine is learned. And the fun part about this is that it also has a global optimum, even though it's a neural network. But that happens because we initialize all these weights here in the beginning of the training, and we fix them. They will never be touched again, and we only learn these weights here, which are towards the output. That's that can be used to basically make the training very efficient. And then here you have some of our results. Basically, what you see here, like are these the spikes here, when the neural network thinks that there is a laughter, and then you see the axis, the red bars here, is when an actual laughter is observed. This is like the human label, and then the blue circles is when we hit that laughter, and we are doing pretty well. Sometimes we just miss it by a little bit, and that's probably because either the network was delayed with its decision, or the label might have been not so accurate. But we get pretty decent F scores and precision and recall values, and yeah, so our F scores are here. The best one is support vector machine, but it's not that much better than these more fun and smaller echo state networks that can be implemented on pretty small devices.
I'm Spike. What's your?
So there's also a whole bunch of other like multimodal data challenges out there. I would like to highlight one. It's called the Audiovisual Emotion Challenge, where the task is to identify affect in a human speaker that talks to a virtual human, and the idea is that we identify like if the person's happy or sad or angry and so on. And well, this is the data, how it looks like.
I'm Spike. What's your problem?
I have a problem.
Is that so? Tell me about it.
Well, nothing's going
I
terribly
suppose you
wrong.
really think you're something. How can you believe that?
I'm not about myself, I'm not spoiled.
But I think you're wrong to be so pragmatic about it all.
Really? Well, you're not always right. I'm not always right. So.
So you use this virtual human to obviously try to induce emotions,
I think
but like
you're too harsh. You have to sit back and just, you know.
Go for it.
so yeah, but the idea is to use a lot of those videos, and then have human annotators annotate them on these like affect-related variables, like valence that we said, like could be positive and negative, or arousal, which in this case is called activity or activation. Basically like high or low activation, or like so low activation would be sad and high activation would be angry and happy, and these kind of things. And so there are multiple sub-challenges: the audio only, video only, and audio-visual. And what the idea is to extract, and there are extracted features, but you can use all these types of features and try to come up with ways to combine these the information streams. In this case, there was like an early fusion that we tried out. It's a paper from 2011, and then late fusion, which basically just combines the outputs of multiple classifiers in that way. And so the LDCRF in this case like outperformed the other classifiers, so that's why we chose the LDCRF instead of like the SVMs, for example, to combine information here. Then that was the winner, but after a year after, we even improved on that result and got like 80% accuracy in the audiovisual challenge for these types of outputs. And you can already like guess, so why is it accuracy if it's like continuous values, like positive, negative, like it's like these continuous domain values. Well, it was basically split by median, like everything that's above the median is considered like yes positive, and everything below the median is considered yes or like no negative or something like that. Just a couple of examples. And
he wrote his life story.
And one last example that I would like to bring before we leave is like we are also using multimodal information to predict or to assess public speaking performances. And the kind of like the motivation for us was this guy here that is participating in the World Championship of public speaking. And I'd like to show a video of like what he does.
He wrote his life story down in a journal with a twist. It was a poem, one long poem from start to finish. And this from a man who never went to school.
So you can see like the guy changes his posture, he walks around on the stage, he like uses visual emphasis as well as acoustic emphasis, he changes his voice. So there's a lot of multimodal happening here. So we wanted to actually build a model that can predict, based off of these performances, if the person is a good or bad public speaker. And what we also did is we actually built a virtual audience so that people could talk to a virtual audience and don't have to talk to actual humans. We had 10 different categories of performance assessment, which included gesture usage, speech, and overall performance. We utilized the same visual features again. We then learned an ensemble tree with, in this case, not a classification output, but a regression output. So we would kind of combine the output of this ensemble tree over, like, for example, in this case, it's like a mean fusion. So you add these together and you divide it by 3. And then we could show that we outperform the visual only and the acoustic only domains significantly with our multimodal approach in all the 10 categories. And we actually and this is the evaluation using correlation between like expert annotations and our outputs. And this is the evaluation based on like mean absolute error. Yeah, so these are some ideas that you can combine into like generic architectures. And like these fusion techniques are basically infinite, and I added a bunch of resources at the end of these slides. I think we had that also in the first slide deck, but just for your reference, you can look at a couple of data sets that are important and machine learning algorithms, etc. Any questions? Okay, this should all be online already. No? Okay, so next week we're talking about deep learning, and we're going to start off with like the idea behind deep learning, and like autoencoders, and then we're going to talk about convolutional neural networks, and then we're going to talk about LSTMs, and then we're talking about generative networks and stuff like that. And yeah, so and next week, Wednesday, we're going to have the basic presentations, right? Okay. Very good.
Can I ask you another question about my project? So, I'm like researching a lot about cats. Like, is it possible if, like in my project, like different applications, like, and like the different models that we use right now, kind of how it would be applied, like applied to like a big
I would just wonder if
It's like, yeah, and you could also try, for example, like you can do a DC GAN, or like instead of like a convolutional neural network, you use a NLP or something like that, and see like what the differences are. Yeah.
And then I was thinking of maybe doing like some type of something where
Okay.
the problem, so I try to
Okay.
so it's just like different uses of GAN.
Sure, sounds good, yeah.